we had another shunt series feedback, and here we identified the feedback network to be this 9K and 1K, and so we had to do a DC analysis. We did a quick DC analysis. We realized that our output is 0, which is good, and then we had to use those DC values in order to come up with AC parameters such as the little RE inside the transistors, because we needed to use them for the gain, right? So we found them. Then we had to find the R11 and R22 from our feedback network. This was the feedback network. R11 was looking into here, shorting the other side. So R1 parallel R2 would make R11. R22 is looking from this side in, keeping the other side open, and that would give us R22. And just bringing it to the amplifier now, this was the newly formed amplifier. We had to find the gain of this. And can someone remind me if I did go fully over all this or not? Because if not, I have to slow down. If yes, then I can go a little faster. Anyone?
No, sir, you didn't end up getting through this. You said you would you'd do it again.
Okay. Okay, sure. All right. Then here it is, the newly formed amplifier, which has 2 stages. One stage is this, the other stage is this. It includes R11 and R22. So all we have to do is find the gain. This would be the gain of the newly formed amplifier. Now, for the first stage, this is pretty much like the one in the midterm, you know, except that was TNP, and then on the second stage it was simpler than this. But then here we have to find the collector resistances and then the emitter resistances to dance Hawaiian, basically, for the gain of the first stage. But the resistances connected to collector node includes 20K to ground, because this 20K AC-wise is connected to ground. And then from the base of this Q3, what we see is all the emitter resistances multiplied by the beta plus 1 of the transistor Q3. So what is on the emitter? It's the 2K and a 10K in parallel, then in series with the little RE of the Q3 multiplied by beta plus 1. That's what we have here. Then it is at this node that we are looking, and then we have 20K to ground as well in parallel. So from right-hand side to ground is this big expression, and from this node up into the 20K to ground, then we have the 20K, which is in parallel with it. Collector resistances is all that we have there. On the emitter side, what we have? Well, obviously the 2 little REs of the 2 transistors, but there's also the effect of 10K, which is in series with the base of Q1, and R11, which is in series with the base of Q2. So we can bring that effect into emitter by dividing them to beta plus 1. So 10 divided by beta plus 1, and 1 parallel 9, 1 parallel 9, R11 divided by beta plus 1. Plus the 2 REs that we have, and this is the emitter resistances. So this is Hawaiian dance that we can do for the first stage, collector resistances over the emitter resistance. Now we have to multiplied by the gain of this other transistor. And if you notice, this is a common collector amplifier. Common collector amplifier has a gain close to 1. But if we want it more exact, then it is the voltage division between whatever resistance is externally in the emitter and the little resistance of the emitter for the gain of common collector or emitter follower. And here it is, the resistance in the emitter, which is 2K parallel 10K, divided by 2 parallel 10 plus RE. So multiplying all that will give us the gain of the newly formed amplifier. That was a big part of it. Okay, done. Any question? Yes, Aidan?
Sorry, could you go back one slide? I just wanted to see the base schematic really quickly. It was just why they got separate. Why when we go into the AC form do the 9K get separated on both sides?
Oh, this is R11, this is R22. So from this we calculate the R11 and R22. Can actually make it larger. Why didn't I? Sorry. It's a part of the feedback network that makes R11 for us. It's also a part of the feedback network which makes R22 for us. Does that answer your question, Aidan?
Well, I'm just a bit confused of how they were formed, like how R1 and R2 are, sorry, how the 1K and 9K on one side is parallel, and how on the other side it's in series, and how they were formed. I'm a little bit confused.
If we go back to this, R11 is formed by shorting the other side, looking into the left-hand side. R22 is by keeping it open on this side, looking into the other side. And that's exactly what we basically had here. So shorting it, looking here, keeping it open, looking there. R11 and R22.
Okay, so because it's two, is it two separate feedbacks that's being split here?
Sorry, two separate feedbacks. What?
Is the reason? Is it two? So this is just using. Okay, I think I get this a bit better now.
Okay.
Right.
You see, R11
I was just confused on whether or not I was different.
Yeah. So we first find what is R11 and R22, and then R11 goes in series with the input of the amplifier. R22 goes in parallel with the output. And that's exactly what we are following here. Yeah. R11 is in series with the input, and R22 is in parallel with the output. All right. So we plug in the values, get the final value for the gain of the newly formed amplifier. Then the input resistance to the newly formed amplifier we have to find. And for that, we have this 10K. And then from the emitter side, we have RE1 and RE2, which we have to multiply by beta plus 1 in order to bring it to the base. And then we have this R11 from the other side. Either we can say from the other side, or we can say that, we bring it to the emitter side by dividing to beta plus 1, and then again to the base side by multiplying it to beta plus 1, and then this appears next to the 10K. So the 10K and R11 and the reflected versions of the emitter resistances to the base give us the input resistance. So this is the total input resistance. This is the 10K, this is the R11, and this is the beta plus 1 times RE1 and RE2. So this is the input resistance of the newly formed amplifier. What about the output? For the output, which is also a little tricky, we have to notice that from this node, which is the base of Q3, and you know, we're looking for the output here. This is the output. The base of Q3, which is the collector of Q2, from this side down is a huge resistance, so we ignore that, the little RO, remember? If you're not given VA, early voltage, then we don't have an RO, we don't have to consider an RO. So what is left to ground is 20K, which is, see, it is in series with the base of Q3. Resistances in series with the base of Q3 or any transistor can be brought into the emitter by dividing it to beta plus 1. Then it becomes in series with the little RE. Now, the base, when we get rid of this 20K, the base is as if it was shorted to ground. So here it is, ground 20 over beta plus 1, and the little RE is at this node. Now at this node, the 2K is to ground and the 10K to the ground, R22. So here it is. Now we're looking in here, if we didn't have this top part, it would be only 2K parallel R22, right? But now we have that top part connected to ground as well from this node. So this will become parallel to 2K and R22. So that's how we get 2K and R22 and the RE and 20 over beta plus 1 all in parallel. And this in parallel with R1, R22 and the load RL. Now, this was the newly formed amplifier things that we need to find: gain, input, and output resistance. Now, if we find beta, which from the same feedback network, we can find that VF over VO is 0.1. The voltage division will give us VF over VO. We have beta, we have A, we can put them together to come up with the AF, the gain with feedback. Okay, and we can use 1 plus A beta times the RI that we found for the newly formed amplifier to get the input with input resistance with feedback. However, unless we take the RS out, it is not going to be the true input resistance with feedback, and that's why we take the RS out of it, and it becomes the true input resistance with feedback. For the output, the same way, the output resistance must be divided by 1 plus A beta to get the output resistance under feedback. But again, we need to take the RL out because RL does not belong to the amplifier, and whatever is left is R out that we need to find. And that will give us the true output resistance under feedback. Okay. So that completes this example, and that concludes our series shunt configuration. Any question basically about how we proceed with series shunt? It was basically summarized here, where we had to form a newly formed amplifier by absorbing R11 and R22 into our old amplifier, the basic amplifier, which also included RS and RL. And then from the feedback network, we had to find R11 and R22 to put next to the amplifier for newly formed amplifier, and as well as beta. As soon as we do that, we have everything to analyze. We have we have this formula to deal with, we have this formula, and we have this formula basically to deal with. And then excluding RS and RL is minor. It's an obvious part of this procedure, but the main part of it is using this formula, finding A, or the newly formed amplifier gain, and the beta, using it in this formula to find the gain, using it in this formula to find the inputs, and in this formula to find the output resistance on the feedback. Okay, Aiden seems to have a question. Yes, please.
Just a quick thing, just to make sure I have this right. Is the reason why we were able to identify that aspect of the filter, basically, or the feedback, being that one side of it is technically the input and the other being the output? I'm trying to say the blue square, being able to... why we were able to identify... Yeah.
So we first look at the loop, find the loop. And the loop is connected between output and input. Okay.
Yep.
So you take whatever is between the output and input as the feedback network, and then do all these sort of things with it to find R11 and R22 and the beta. And then all you have to do to find the gain and put them together as in order to find the gain with feedback, input, and output, like that. Is that what you were asking?
Yeah, I believe so. Because you could have technically gone. Could you have technically gone with the other input on the other side?
No, because that's not in the loop. You see, this is outside the loop. What is connecting this to the output? Nothing. But this input is connected to the output through this network. Yeah. All right. Sayed, question?
Yeah, I just wanted to ask if you could clarify the true input resistance and the output resistance one more time.
Oh, these two input and output. So, you see, when you find that the newly formed amplifier, these three things are what you need to find. The gain of the newly formed amplifier, the input resistance of the newly formed amplifier, and the output resistance of the newly formed amplifier. But this is not your input, output, or the gain with feedback. This is just the amplifier. Now, you come here after you find the beta, using this formula will give you the gain with feedback. Using this formula, which means the same Ri that you found on the newly formed amplifier times 1 plus A beta will give you the input resistance with feedback. And this way to find the output resistance with feedback. Okay, but these are not the true output and input resistances that we have under feedback, because we have an RS on the input side, which does not belong to the amplifier, and an RL on the output side that does not belong to the amplifier. The reason we included them in here was because we wanted the network look like ideal situation. In ideal situation, we did not have these resistances, RS and RL. What did we have? Basically nothing. No RS, no RL. And that is how we started analyzing the series shunt. And we learned from that you know, the input resistance is calculated like this, the output resistance is calculated like this. And under that condition, this was true. A over 1 plus A beta. When there is no extra components, just the amplifier and the feedback network. Now, when it came to the real situation where where we would have some source resistance as well as load resistance in the system, it would upset that ideal situation. Now, if we could bring this into the amplifier as well as this, and any other non-idealities due to this feedback network, then perhaps we could make it look like that ideal situation that we had up here, right? So this has been the trend. This has been what we've been trying to do in the examples, whether this one or the next one. And it will be the trend all the way to the end of the feedback network, except for every type of feedback. We will have to deal with different type of amplifier. And, in some cases, R11 goes in series, sometimes in shunt. R22 sometimes goes in series, sometimes in shunt. So it's just a variation of the same procedure. And if you get it in one, which is this one, series shunt, it will be a lot easier to get it in the other three remaining types. Does that answer your question, Fayed?
Yeah, that answers my question. Thank you.
All right. Okay, so we are ready to progress with the next type of feedback, but go ahead and send me your name, please. Thank you. Thank you very much. And I get to change my sharing window. This one, yeah. Okay. Yeah, thank you for your needs. Let me copy it. Now we're going to be talking about series feedback. And once again, we will deal with ideal situation first, and then expand it to non-ideal situation. But what we have is both at the input side and the output, the two port networks connected in series. Okay, look at the amplifier, and the model is changed. And that is because we are actually amplifying a voltage into a current on the output. So the output side should be current, which is dependent on the input voltage. Okay, in fact, this is a transconductance amplifier. This amplifier is a transconductance, current on the output, voltage on the input side. But we can still use the gain with feedback as gain over 1 plus gain times beta. However, notice the gain that we are talking about is an I over V. It doesn't have to be V over V all the time. Okay? For the voltage amplifiers, we had V over V, but we could actually have a current which comes out of our amplifier while the input is a voltage. So here we are dealing basically in our feedback loop with I over V, okay? So both in the original amplifier and at the end when we are dealing with the gain of the entire network under feedback. And this would be the final result, the model for the amplifier with feedback. It has an input resistance under feedback, output resistance under feedback, and the gain of the entire amplifier on the feedback. Now, because we have series, and we had seen that when it is in series, the input resistance becomes multiplied by 1 plus A beta. So the input resistance of the original amplifier must be multiplied by 1 plus A beta to get the input resistance with feedback, which means the input resistance that the source is viewing into this system. Now, this is new that we have series on the output side. So what we need to do is to find out what happens when we have that situation. Basically, here is what we have. In order to find the output resistance of the system on the feedback, we need to apply a source, and here we have applied a current test source, a test current source, and we have to find the voltage across it in order to find the resistance. That resistance is the output resistance under feedback. Okay. Now, on the input side, when we come and do this, we need to kill the input source. If we kill the input source, you see KVL in this loop says that VI becomes negative VF. Okay, if this is 0, VI is negative VF. So, VI being negative VF, VF is beta IO, and IO is actually the same as IT, because this is the current which goes through the system, the entire output loop. So replacing, or actually if we look at the voltage that is dropped across the current source, which is the same as this voltage, it's this test current deducted from it AVI, which goes through RO, so times RO, that would be V, right? That's what we have here. Now, replacing this, or the VI with minus beta IT, and then we can factor out IT, and then bringing it underneath V on the other side, what it leaves is 1 plus A beta times RO as the output resistance under feedback. Which makes sense because, you know, when we had previously, we had, or even on the input side, when we had the two in series, we realized that we will get the input resistance, the original input resistance, scaled by a factor of 1 plus A beta. And it does make sense that we get the same thing on the output side when they are in series. And it makes it easy to remember, you know, when you have series, your resistance increases. But by how much? By a factor of 1 plus A beta. Okay. Now in practice, what we have? In practice, we have RS and RL. So once again, we have to absorb it into the amplifier, the basic amplifier. But the feedback network, what should we use in the feedback network is now the Z parameter, because it's only Z parameters that has series components on both sides. And it makes it easy to push the resistances up to the amplifier from both sides. See, Z22 can go up the amplifier on the output side, Z11 up in the amplifier on the input side. So now when we do that, the resistances go up, and then what is left is this source which is talking about I1 coming onto the output side. And if we believed that we do have a unilateral system, which means the feedback network is going to pass only from right to left, not left to right. So we can ignore this. Ignoring this means killing it. And killing it means short-circuiting it. So we short-circuit this. We have the beta I2 as the sample produced to be added to the input side. And we've gotten rid of the resistances, the Z11 and Z22. We placed them into the amplifier. So what we end up with is this, which, if we consider all those extra resistances inside a new amplifier now, this would be our newly formed amplifier, we will see that the feedback network is idealized now. And then when we find everything, all we have to do is to take the RS and RL out of the resistances, the input resistance with feedback and output resistance with feedback. And because we have series combination here on both sides, it's a lot easier. We just subtract it, right? So this would be our newly formed amplifier, and this is the idealized feedback network. Okay, so once again, here it is. What we have is a basic amplifier in which we are including RS, R11, R22, and RL. Now, the R11 and R22 can be found using Z parameters, Z11 and Z22. And for that, we keep the other side open, look into this side. Or we keep this side open and look into the other side for R22. Beta is VF over IO. Remember, amplifier was a transconductance amplifier. Beta is always opposite to that, because the signal going through the loop must feel no dimension, doesn't have to care if it is in ohms, in Siemens, in kilograms, in meters, in whatever, no units for the loop. So this must cancel whatever that amplifier is giving us. This is giving I over V times V over I becomes unitless. So beta is the V over I. And that's also what we can calculate when we have beta, when we have A from the newly formed amplifier, then we can find everything else. A with feedback becomes the A of the newly formed amplifier over 1 plus A beta. The input resistance becomes the input resistance of the newly formed amplifier times 1 plus A beta. The output resistance with feedback becomes the output resistance of the newly formed amplifier, again times 1 plus A beta, because we have both them in series with the input and the output. Now, here we have an example for that. An example that includes a 3-stage amplifier. And, we are given, for the ease of analysis, always you first need to do a DC analysis, but to make it easy, we're given the DC values for the transistors. Okay, and obviously we look at the circuit, we find the loop, and the loop is not anywhere that we can call output voltage, but basically it is the current which comes into this network, and then a voltage is produced which goes in series with the input, like that. Okay, so it is current on the output side and voltage on the input side, And these are the components of the feedback network. Okay, so far so good. Another thing is that this beta that you see for transistors identified as 100 is called beta F. Either that or HSE is another way of expressing the current gain of a transistor, so that it is different than the beta that is a characteristic of the feedback network. The feedback factor beta, to distinguish that from the current gain of transistor, we call the current gain of a transistor beta F or HFE. Okay. Remember that in AC, all these are going to be grounded. Okay. And now, after we identified the feedback network, all we have to do is to use it and find R11 and R22. So we keep this side open, look into this side, left-hand side, and we see the RE1, which is in parallel with the series combination of RF and RE2. Okay, so that makes the R11. If we look into the right-hand side, keep the left-hand side open, we have R22, which is RE2 in parallel with the series combination of RF and RE1. Okay, so we found R11 and R22. Now we have to put it next to the amplifier, which are the transistors, basically. On the input side, R11, and on the output side, R22. Then it forms the newly formed amplifier. And now we have to find the gain for it, which is IO over VI. IO is here, VI is on the input side. Now, notice that we are dealing with the feedback loop and whatever gain that feedback loop gives us. So, once again, there is no output voltage here. However, we might look for a voltage called the output voltage of this circuit, not the loop, somewhere else. And we might have to find that voltage with respect to the input. After we take care of the loop and the amplifier and everything that we know as a fixed procedure to deal with feedback networks, then we can relate the results to something like that which is external to the loop. Okay, so here we are after the IO, which is basically the emitter current of Q3 over this VI, IO over VI. We can open it up like an accordion, and we can get the three stages gain, or the gain of each stage of this three-stage amplifier. But the first stage is a voltage gain. The second stage is also a voltage gain from base to collector. But the third stage is not a voltage gain, and it is a current over voltage. So we have to find each one of them in order to get the IO over the VI. Okay, let's go one by one. The first stage is pretty simple, as it is the Hawaiian dance that we are applying. And the Hawaiian dance says collector resistances. Resistances connected to collector node. What is it here? It's RC1 going to ground, because you see we have ground up there everywhere. And then from right hand side we have R pi going to ground, R pi of Q2. So R pi 2 in parallel with RC1 is what we have in the collector. What do we have in the emitter? In the emitter side we have the little re and R11. And here it is, little re and R11. And this is basically Hawaiian dance. Of course, there's always an alpha and minus that we don't really care much, because alpha is 1, minus is just the sign change, right? But the major part of it, which is the collector resistances over emitter resistances, is what we call Hawaiian dance. And numerically, it is about 15 volts per volt. Now, for the second stage, also Hawaiian dance works. However, we have expressed it here in terms of GM-RC. Remember, GM-RC, GM could be written as 1 over RE, and then it would become again collector resistances over emitter resistances. In this case, though, the collector resistance is a little more involved. And the reason is that the resistances in the emitter of Q3 are also, or they also have to be reflected to the base, which is where the collector node of Q2 is. So starting from the emitter of Q3, we have the little RE inside Q3, and then we have this, which is R22, so little RE and R22. We must multiply that by beta plus 1 of the transistor Q3. So HFE or beta F, whatever you want to call it, that's what we see from this node to the right-hand side with respect to ground as a resistance. Now, from up here, we also see RC2 connected to ground. So the two become parallel. And then times GM or divided by RE is the gain for the second stage. When it comes to the third stage, as I said, is not a gain, is not a voltage gain. It's the ratio of a current over a voltage. Now, IO, as I said, is the same as IE of Q3. And VC2 is the same as VB3. So if we draw the T model of the transistor, of this transistor, what we have on the emitter is the little RE in series with the R22. Here they are. This is them. Connected to the base in the T model, right? And what's the voltage across them? Is whatever VB3 is. Okay, so VB3 is across a resistor, which is the series combination of these two. And IE or IO is going through it. So IO times R is giving us VB3. So if we divide IO by VB3, what do we get? 1 over R, 1 over R. This R is this R, whatever is in the emitter. And therefore, this part of the gain, which is this last part, is going to be 1 over all that resistance. And it gives us a value of about 10.6. Now we multiply all that together, the 3, and we come up with the gain of about 20 amp per volt. I over V, remember? So this is the transconductance gain of the newly formed amplifier. Now from the feedback network, we have to find the beta, and beta is VF over IO. Okay, here it is, beta, VF over IO. To see how this turns out to be right, we need to look at the feedback network like this. Now this current, IO, comes into these two branches, RE2 in parallel with RF and RE2 in series. So this is the current division that we get in order to come up with IRE1. Okay, the current that goes through RE1 in that case. So here it is. Now, that current times RE1 give us the V across RE1, which is the same as VF. So here it is, that current times RE1. Now, if we bring the I/O under VF, then this is what we have here. Okay, so that's how we get the beta for the feedback network. And then we had A, so we have AF, A over 1 plus A beta. Okay, but if you're interested in the gain of this circuit as the collector potential over the input voltage, VI, then we have to find a relationship between what we found as the output current with this that we call the output voltage of the circuit, not the loop, okay? So we have to distinguish between the loop and the circuit. They both have output sides or places, okay? But with our feedback analysis, we take care of the loop. And then we can extend that knowledge to anywhere else. And it is easy to find the output voltage versus input voltage here of this circuit, because this I out is I emitter, which is pretty much like I collector. If beta is large, it's exactly I collector. So usually beta is large, and we can assume I emitter is I collector. Now, I collector times this R will give us the VO in AC. So if we are looking for VO over VS or VS or VI, so it's VI. Okay, well, the VI and VS are the same here basically, because there is no resistance, you know, there's no resistance separating the input of the amplifier and the source. But anyways, the output part of it, which is I collector times RC3, is the same as I out times RC3, and IO over VS, IO over VS or IO over VI in this case, is found before. So if we multiply that by RC3, AF times RC3 will give us a VO over VS that we are looking for. Now, for the input resistance Rin of the newly formed amplifier, we basically have to consider the reflected version of all the resistances in the emitter of Q1. And what do we have there? It's R11 and the little Re of Q1, which must be multiplied by beta plus 1. And here it is, HSE plus 1 times the little Re and the R11. And that gives us the input resistance of the newly formed amplifier. Now, multiplying that by 1 plus A beta will give us the input resistance on their feedback. And you see it is huge. It's great for an amplifier whose input is taking a voltage in to have large input resistance, because that means the majority of the input source, the voltage of the input source, goes to the input of the amplifier. Of course, in this case, 100% of it goes because there is no RS. But in most cases, we do have an RS, and then that's when it's best to have the input resistance of the amplifier as large as possible. In fact, because we don't have an RS, we don't have to extract RS or anything else from this, and this is the true input resistance into the amplifier. What about the output? The output is a little challenging because it's practically did I go too far? I think so. No? All right, yeah. So the output, when you're talking, the output resistance is the output of the loop. So you see the loop, we need to break it here, look into it, as the output resistance of a series on the output side. So if we do that, this is what we have, you see. So the first thing we see looking up is the emitter resistance of Q3. Then on the base, we have RC2 going to ground. RC2 is in series with the base. We can bring it into the emitter side by dividing it to beta plus 1 or HFE plus 1. When we do that, the base side is now shorted to ground with nothing because we took this to the emitter. So here it is, R emitter and RC2 over beta plus 1. Now the base is connected to ground. From ground is connected to the other side, where we only see R22 to ground. So from this other node, we see R22 to ground. So basically, R22 and the series combination of these two is what we view as the output of the loop, output resistance of the loop. Okay? Now, this is just the output resistance that we see from the loop in the newly formed amplifier. Okay? Now we have to find and this is what that is, the little emitter resistance, the RC2 divided by beta plus 1, and this was R22 here. Okay, but we have to multiply that by 1 plus A beta to get the output for the feedback network, not just for the amplifier. When the amplifier is in the feedback, which indeed it is, we just separated parts of it to form the newly formed amplifier to find the gain, and then we had to put it back into the network for finding the other characteristics of that network. And RO with feedback is one of them. So the RO that we found here must be multiplied by 1 plus A beta. And what that gives us is a resistance in here on the output side of the loop that we see as the output resistance with feedback. But this is not what we have when we look in the collector of Q3, which is where the output of the circuit is. So what we need to do for that is to use I need to stop sharing, and then I need to look at this one, and I need to share this one. Remember when we were talking about current sources, we were looking into the resistance that we view on a collector of a transistor that has a resistance in the emitter. And this is the final equation that we came up with, or actually we did manipulate it furthermore for this special situation, and we got into this. But that's not true for all cases. But this is true for all cases. The very first line that we have here. And if you look at this, instead of RE, if you place ROF, okay, you get exactly what we have shown in this one. So I need to share the previous screen again. And that is this one. So this is exactly that formula if you multiply 1 by this and GMRO by this, and then factor out RO between these two, you get exactly the same formula. Now, this R out shouldn't be called R out, but we're running out of ways of showing output resistances. So, but this is the output resistance of the circuit, not the loop output. Okay, the circuit, and you see it is huge. It's huge. Now, what we just found is that the output resistance viewed into the collector to ground, which was huge, right? But if you're looking for the resistance that we see on the output node of the circuit, again, it's not the loop, the circuit output. Then we also have this RC3 in parallel with it, because that also goes to ground, right? And because this is huge, we can actually ignore it, and that would be this as the output resistance. So even though we went through the trouble finding the output resistance viewed from collector to ground, but because this is huge, when it comes to the output resistance of the circuit, it's the RC3. So yes, we did find the output resistance, but the real output resistance of the entire circuit is that RC3, and finding this is not necessary. So at least we realize that this is going to give us a very big resistance in the collector to the ground, which when it comes in parallel with a smaller resistance, we can ignore it. Okay, so this is, I think, the end of series, yeah, series configuration. Any question? Aiden.
So just to be clear, the output resistance we were finding for the final was the R out of the entire system, not the R out of the feedback?
Exactly. So, we had a loop to deal with originally, right? This is the loop that we need to deal with it, and this is the loop that we've learned, we've been trained how to deal with. Okay, after we take care of everything in this loop, then we can relate it to other parts, like the output terminal that comes out of this circuit. That is not the output of the loop. In fact, output of the loop is not in the shape of a voltage, it's in the shape of a current, right? Excuse me.
Yeah, that's the reason why the output resistance isn't seen as like a point, which would make them in parallel. It's seen as series because it's a current.
Yeah, here is in series, but out here, whatever we find looking down, oops, my internet is getting bad. Let me quickly copy paste your needs. And if I get interrupted or disconnected, I'll come back in a minute. Okay? Do you hear me? Okay, everyone? Hear me? Okay?
We can still hear you, sir.
Okay.
Yeah, we can hear you.
Me, go ahead and type me, and I continue answering Aiden's question. Yeah. Okay. Thank you, everyone. Thanks very much. Yeah. Let me now copy paste it. Okay. So yeah, we always deal with the loop first. We find everything, the gain, the input resistance, the output resistance from the information that we have in this loop. And then now, if we have to extend it to some other points, we can. In fact, in the next topology, you will see that on the input side, we can also extend it the way that we want. But it remains to be seen, and we'll explain it next time. But what I'm saying is that we need to make sure that we understand where is the loop and what's the loop demanding. The loop is demanding an input voltage and output current. Okay, but a voltage somewhere else that we call it the output of the circuit as the voltage can also be related to whatever we find from this loop. And in fact, that's what we did in this example. When we found the gain, the transconductance gain, we could relate it to the voltage gain for the circuit. The transconductance gain came from the loop, but the voltage gain is for the entire circuit. And that's what we found. Aiden, do you have your hand raised from before, or?
Yeah, no, I have one actually quick question. Just because for this type of question, the reason why we were able to consider that part, the output current, am I assuming that because we're allowed to, because beta is really big, because we're assuming IE and IC is the same, we're allowed to assume that's the output current?
Sorry, which slide are you referring to?
It would be going back to specifically when we were creating the loop.
When we were having the loop? Here?
Yeah, right here. So because we're able to assume that the output current is on the emitter, is that because because of how big the beta value is? We're allowed to assume that the IC and the IE are the same, so it's like the output current?
No. Basically, IC and IE are related by alpha, remember? So alpha is close to 1.
Yeah, sorry.
So that's why we can say that IC is almost IO.
Yeah, see, the point I'm trying to get at is that if we get into that scenario where because alpha isn't close to 1 anymore because your beta value isn't high enough, so your alpha actually gets small.
In that case, you can actually include alpha as well. So IO over VS, now becomes IC is going to be IO times alpha. Okay, so when we get to writing this part, multiplying IO by RC, there is also an alpha involved.
Okay.
That's all.
Okay, I thought something else might have changed potentially in terms of where we had to look at our loop and our connection point.
No, we have a simple relationship between IC and IE, and we can even make it simpler by ignoring alpha. But if you want to include it, okay, it's something less than 1. Yeah, close to 1.
Okay, I was just thinking in the odd cases when alpha isn't close enough to 1, but because we can relate it by it, it shouldn't matter. Okay.
Yeah, exactly. You can do that. But here we are assuming that it's close to 1, which I think was beta given 100?
Yeah.
Beta,
feedback data was given 100, but we never stated.
Yeah, here beta is 100, which 100 is almost I collector and I emitter the same. Yeah. All right. Yes, question. Go ahead. First of all, I have a question. How do you say your name?
Blue is fine.
Blue, what else?
Just blue is fine.
Oh, blue is fine. Okay. Blue. All right.
Could you go to the next slide?
Next slide.
Yes, please.
Yeah, this one?
Yeah, so when we were doing the Hawaiian dance for Q2, how come, where's the RE2?
Oh, well, GM, let me see if I can write it here. GM2, right? Here we have GM2. GM2 is actually exactly equal to alpha over RE. But alpha is almost 1, so it becomes 1 over RE. Then if you replace 1 over RE, or replace GM with 1 over RE, then it becomes collector resistances, which is all this, over the little RE, which is emitter resistance. And that's the only thing we have here, the little RE. Does that make sense, Blue?
Yeah, that's fine. Thank you.
Yeah. All right. Any other questions? Yes, Aidan, please.
Oh, just a quick one. This might come up from the tutorials, but the tutorial teacher said the midterms were looking really bad. Do you have an idea of how they were doing?